Okay, so here we are on topic 5.2, and it's the Voronoi diagrams. We did some exercise once with one of these. I don't know if you guys recall with a whiteboard and stuff, but we're going to go a little bit into more detail of what these Voronoi diagrams are. And here we have an example of how they are used. So it says, emergency location services sometimes try to locate individuals based on their mobile phone signal. The first step in this process can be to locate the individual based on the nearest mobile phone antenna. A map to identify service regions for each mobile phone antenna would look like something on figure 5.3. So in this case, each red dot, that you can see here, is a mobile phone and tower. And the blue lines are the boundaries of each region served by that tower. So these are the boundaries, as we can see. So this is an example of what is called a Voronoi diagram. The polygons on the map, each of which shows the service area for a particular mobile phone antenna, are called cells. So these are called cells. Now notice that it's a good name because they do follow a cellular pattern. They do look like a little bit like cells, where this would be the center of the cell, the nucleus of the cell, right? The dots represent mobile phone antennas and are called sites. So these are known as sites. The line segment boundaries between each region are called edges. And places where edges intersect are vertices. So this is an edge, and this is a vertice. An edge, vertice, edge, vertice. So here we have three edges on this vertice. Notice that some of the edges of cells around the outermost sites are actually rays and not line segments. So that means that here, this goes on. Okay, so this is a brief introduction to the Voronoi diagrams, and now we're going to actually solve some exercises with them. Okay, so here we are on example 5.4, and they say using the Voronoi diagram, A, identify the site closest to 30, 20. So we have to go to the grid here and look for 30, 20. So that's just the intersection point between these two lines, right? The one that starts here, 30 and 20, and we're going to see that that's going to land more or less here, right there. So this is within the cell that contains site A. So site A. Now the interesting thing about these Voronoi diagrams is that if you are within the cell, the closest site is going to be the site within the cell. And that's just because of how these things are built in principle. Basically what I'm saying is that the way these are built is that you're going to have, for instance, this distance from A to this line at this point will equal the distance from D to that line as well, to that point on that line that separates the cells. Okay, and this line is called edge, remember. So this edge, if you draw a point on this edge, it's going to be equidistant from the point to A or the point to B, or the edge to A or the edge to B. We'll see why in a minute, okay? So it says here, give the coordinates of a vertex equidistant to 4 points. Now, precisely because all these points are equidistant, right? If I have a point on one of these edges, it's going to be equidistant to the sites within the bordering cells. But now all I have to do really is look for not an edge, but a vertex. And it has to be a vertex surrounded by 4 sites, or 4 dots. And we can see that that vertex is right here. It's this one. Because as you can see, that vertex is surrounded by sites M, F, G, C. And that vertex is at approximately 20, 5. So that would be the coordinates of that vertex. Part C says estimate the coordinates of a point equidistant to sites A, E, and K. So we need something that is close to E, A, and K. It has to be on all those three sites, cells, edges. Okay, what do I mean by that? So for example, here we have an edge that is shared by E and K, but not by A. But this vertex here is, right? That vertex is shared by E, A, and K, and therefore that point has to be equidistant to those three sites, A, E, and K. And let's estimate that coordinate. Now, please forgive me because I cannot see those lines too well, but it seems to be 19 here, and I'm going to guess about 26 and a half. So let's say 19, comma, 26 and a half. Okay, part D, explain why the diagram cannot give us a point equidistant to sites C, F, I, and L. So let's look for C, F, I. Now I is far away. I and L. So that's the reason, right? It's out of range, so to speak. So I does not share any edges with the other cells. Letter E, point AA is equidistant to sites J and N. Find the value of A. So A has to be equidistant to J and N, and not only that, it has to be in the form A, comma A. Okay, so let's look for sites J and N, and we can see them up here. So this is J, and this is N. Now, a point that is equidistant is somewhere here, but what we need it to have is coordinates that are the same. Notice that 40 is very close to that, right? 40. So here, if we take 40, we land on that edge, and let's see if that coincides with this other 40. Would it? Well, yeah, here's 40. And I think it would coincide. Yeah, definitely. So that means that A has to be 40 because that point there, this point here, is 40, comma 40. And because it's on the edge shared by J and N, it is definitely equidistant to both sites. And you can intuitively see it here on the graph. You can see that those distances are equal. Okay, for F, I'm going to use another slide because it's a totally different level of question. I mean, don't get me wrong, it's easy as well, but it requires a little more work. Okay, so here we are on another slide to solve part F of the question. So it says, find the equation of the edge between sites E and K in the form y equals mx plus c. So it's a linear equation. And we have to find sites E and K, which we can see that are here, right? E and K. So basically they want us to find the equation for this line, this edge. Now here's the interesting thing about these Voronoi diagrams, and it's that these edges dividing each one of these sites, no matter which edge you look at, it's going to be dividing the two sites that are perpendicular to that edge in an equidistance fashion. So what that means is really that this is just a perpendicular bisector of these 2 points, of points E and K, for example. That's the one we will have to find, right? So look, if I draw a line from E to K, I can see that it's perpendicular to their edge. And I want to find the equation of the edge. But I can use the slope of this line, the one that goes from E to K, to find the slope of the perpendicular. So let's do that. All right, so the slope from E to K would be 28 minus 18. Let's call this M1, slope 1. So 28 minus 18 over 8 minus 12, and this is going to equal 10 over negative 4, and this is simplified negative 5 halves. Okay, so if this is the slope of the point between, or the line between points E and K, the perpendicular to this, which is M2, remember this property, if this is minus 5/2 and I multiply it by the slope of the perpendicular, it should equal -1. So if you solve for M2, you're going to see that it is the opposite reciprocal, or the reciprocal with the opposite sign, and that's positive 2/5. So that's the slope. So once we have the slope, all we need to do really is plug in a point on the line. But what point is on the line? They don't give us any points that are on the line. I'm talking about the perpendicular bisector. But we do know that this point here, the one that is on the intersection of the two lines, is the midpoint of E and K. So we can find that midpoint. And remember that midpoints are simply found by adding the coordinates and dividing them by 2. So the midpoint would be 8 plus 12 for x divided by 2. And the other one would be 28 plus 18 divided by 2. And therefore, the midpoint was going to be 20 divided by 2, 10, and 46 divided by 2, 23. So 10 comma 23 is a midpoint. And we can see that that's probably right? This is 10 here and 23 on the y-axis. So yes. So we have gathered enough information to finally write the equation, because the equation is in the form y equals mx plus c. We already have m. Y equals 2/5 x plus c, and all we need to do is find c, but we can use the point we just found to solve for c. Let's do that up here. So that would be 23 is equal to 2/5 times x, sorry, that's times 10, plus c. We can solve this very quickly, and we can see that c is equal to 19. Okay, that means that we have the equation. I'm going to rewrite it somewhere here so it doesn't look so disorganized. So the answer would be y equals 2/5 x plus 19. So that would be the equation of the edges between those two sides, which is the perpendicular bisector. Okay, so the next slide goes into how to construct Voronoi diagrams. And they talk about a variety of algorithms or methods to construct them. And it talks about a method called the incremental insertion algorithm. Now that sounds awfully complicated, and they give you a series of steps and make it sound like it's very difficult. But basically what you do is that you choose a couple of sites, draw a perpendicular bisector between them, and then start building the new edges. And that's what we're going to see in the following example, which will explain this in a much easier fashion. Okay, so in example 5.5, they ask to show the process for adding the site shown in red to the Voronoi diagram. Okay, so basically we're going to see the process of building new walls or new edges for this site. So notice here that we have the first step, which is simply to identify the nearest site. So in this case, we identify this one. And step 2, add a perpendicular bisector, which you do as a dotted line. And then the third step is that you use that perpendicular bisector to create a line segment, but the endpoints are going to be on existing cell boundaries. So you go from this cell boundary down to this one, and you simply build that edge. So the reason this is called an algorithm is because you repeat the same process over and over. So what we have to do is choose another site and draw a perpendicular bisector. So in this case, notice that this is the other site chosen, and the dotted line is a perpendicular bisector. Following that, we draw the segment, but from one edge to the other. So that's why you start here at this edge and then continue down to this other edge and stop there. This was the one that we drew previously. Okay, and as an algorithm, it repeats itself. And we do the same process again, but we choose this other site And notice that the dotted line is the perpendicular bisector. Then we continue with the same process by drawing the line segment from edge to edge, from here to there. Notice that we had these two before. And then finally, the last site that we have to draw a perpendicular bisector with is this one. Draw another line segment from edge to edge, and we end up with the figure. Now, the last step would be to get rid of the edges that are inside, and that's what we're going to see on the next slide. And there you go. You can see the new cell that fits perfectly into the figure, and after we have removed all the edges that were inside. Okay, so here we are on example 5.7, where they ask us to create a Voronoi diagram for the points A, B, C, and D. So in this one, basically they're asking us to create the diagram from scratch. So the first step is choosing 2 points. So we're going to choose A and B. And then the next step would be to build the perpendicular bisector between A and B. And we're not going to even use any algebraic equations or anything. It's just going to be a drawing where you have a line that you know is a perpendicular bisector between A and B, and you should get something like that. And then this line is made continuous because this is going to be the first edge. Okay, next, another perpendicular bisector between points A and C. So between points A and C, you get that perpendicular bisector. And then you're going to draw a line segment that starts on the x-axis and ends on the already existing edge, and you get this. Now, we should build another perpendicular bisector between C and B. And this is what you get. So that's a perpendicular bisector between C and B. It happens to go through point D, but that's just a coincidence. As we do this, we have to get rid of any part of the perpendicular bisector that is not necessary, right? That is not necessary. And also we have to draw the red line, and this is what we get. Okay, so we have to get rid of sections of these lines that have no function, like that extra segment which is within the cell for site C. So we should get something like that. And then to finish, all we need to do is build the perpendicular bisectors between sections B and D, as well as C and D. And there you go. Very well, so on the next slide, we're going to see a reference to something called nearest neighbor interpolation. And that is simply a common use of the diagrams, of the Voronoi diagrams, which is to assign values to points based on the nearest site. So this is called the nearest neighbor interpolation. And that's what we're going to go over next. It sounds much more complicated than what it actually is. As we're going to see in the next slide, it's actually fairly simple. So, for example, consider the map in figure 5.5. In the map, we can see measurements from rain collection gauges on 27 July 2017 in Pueblo, Colorado, USA. The measurements are given in inches. If we want to estimate the rainfall at a location near one of the rainfall gauges, we can simply use the nearest gauge. Okay, so if you look at the map, the lines are not edges of cells. These are actually road maps. So that means that if we had to answer something like this, we would have to build the Voronoi diagram. And that is precisely what they ask us to do in example 5.8, where they say use the map of rainfall measurements in figure 5.5 to estimate the rainfall at the coordinates P6, 4. So let's suppose we did it all. Let's just go to the solution. And you can see that here they have the actual cells and edges around the sites of the Voronoi diagram. And point P is right here, which is in the cell that contains this guy here. And that site is 0.63. So that would mean that we could estimate that for site P, the rainfall would be 0.63 inches.